So let's go ahead and do this in Excel. I have a starter file related to what we've been working on in previous screencasts. I've got our equations, I've got our data here. I've named a couple things. We have n, which is the count of y. That's the count of our y vector. I have k, which is just the number of parameters. We have 4 parameters here, which is just the number of regressor variables. We have 4 regressor variables, and I've calculated my sample average. The degrees of freedom, remember, for regression is k, so I'm just going to put in equals k. The degrees of freedom total is n minus 1. The sum of the degrees of freedom for regression and residual have to sum to the total degrees of freedom, but you also know from what I went over earlier that the degrees of freedom for error are n minus p, or n minus quantity k plus 1. So let's go ahead and do that, n minus quantity k plus 1, and that equals 20. So these two degrees of freedom, regression and residual, or error, should add to the total. I can calculate my sum of squares for the regression, that's SSR. Now I'm going to use this formula here. I'm going to rearrange to calculate SSR. Let's calculate residual sum of squares. I've already calculated my residuals over on the left, so this is just sum squared of our residuals that I've named RES, and that's 1039. SST, remember earlier I told you that a shortcut for that is to use the variance.s formula of our data times n minus 1. That's a shortcut for calculating SST. And then the regression sum of squared, we can use this equation up here, and that's just equal to our total sum of squared minus our residual sum of squares, 9739. Now we can calculate our mean squared for regression and residual, or error. I'm going to go ahead and name this SSR. I'm going to name this SSE. And we can calculate our mean squared of the regression and error. That's just the ratio here of SSR divided by k, using this formula up above. Residual mean squared, or error mean squared, is equal to SSE divided by quantity n minus k plus 1. And that's equal to 51.9. Now we can calculate the test statistic. This is our ratio of MSR to MSE, and that's just MSR divided by MSE, which is 46.871. And finally, I can calculate a p-value. We compare this to the F distribution, and this is an upper-tailed test always for this ratio because the numerator must be much, much larger than the denominator. And so I'm going to do the F.dist of our F statistic with k degrees of freedom in the numerator and n minus quantity k plus 1 degrees of freedom in the denominator, and we get about 6.9 times 10 to the negative 10th. So all of this that I just did is output in the regression output, and if you compare, you'll see that we get the same exact thing when we perform with the regression tool in Excel. So now you know how to calculate this entire ANOVA section. I've already gone over how to calculate these test statistics and p-values for simple linear regression, but let's now do this for multiple linear regression. Here we're going to perform a hypothesis test on individual regression coefficients. We set up our null hypothesis. The jth coefficient of our regression model is equal to some value. Oftentimes this bj0 is equal to 0. We want to see if it's other than 0. We set up an alternate hypothesis. It's not equal to 0, for example. And so our test statistic becomes the following. We're comparing or dividing by the standard error of that coefficient. Recall from a previous screencast that we can calculate the standard error using the square root of our standard error squared times the jth diagonal element of c, where c is just x transpose times x, and we take the inverse of that. So we can use that. We can calculate standard error in the denominator, calculate our test statistic, and since this is a two-tailed test, we can compare the absolute value of that to t alpha over 2 with n minus p degrees of freedom, and if that's true, we accept the alternate hypothesis. So let's go ahead and do this in Excel. I've got my coefficients that we've calculated previously and our standard errors of those coefficients. I'm going to use this simple equation to calculate our test statistic. That's equal to our coefficient divided by the standard error of that coefficient to give us our test statistic based upon the t-distribution. I can pull this down, and now what we can do is calculate p-values. Again, in Excel doesn't know if you're doing an upper-tailed or a lower-tailed test. It just automatically does a two-tailed test. If you want, you can do an upper-tailed test. It's more typical to do two-tailed tests when analyzing significance of the regression coefficients. We can use the t.dist.2t function, which calculates a two-tailed p-value, our test statistic with n minus quantity k plus 1 degrees of freedom, and we end up with a p-value of about 3.8 times 10 to the negative 16, and we can easily pull that down. We need to actually make this an absolute value because we're looking at the absolute value of that, and now we can pull this down, and those are our p-values. You notice that those are exactly what we get using the regression tool, so these p-values. Now, what this is telling us, if we look at the p-values, you see that beta 3 and beta 4 have p-values of 0.89 and 0.24 respectively. The conclusion that we make is that those two terms, if we look at our model here, those two terms are not significant. And if we look at what x3 and x4 are, that means that whether or not the procedure was a surgical procedure or a medical procedure, that has no bearing on satisfaction, and neither does anxiety. Only these first two, age and severity, have a bearing on satisfaction. So that's our conclusion. In conclusion, in this screencast, we worked through hypothesis tests, both on the significance of the regression model as a whole, but also hypothesis tests on the significance of individual terms in your model.